Welcome to the second part of the control system studies. This part of the study will basically cover the frequency domain analysis, the stability studies, and the issues related to the control systems design. So today's session will cover mostly about the polar plots and its details, how to draw the polar plots and what are the different kinds of polar plots we'll study in today's session. So this will have a series of episodes on the second part of the control systems, and if you need to follow up and be in touch, you need to subscribe this channel. So today's outline is the introduction to the frequency domain analysis, basically why we are doing the frequency domain analysis, the polar plots as is obtained from the fundamental ideas of Nyquist criteria. So we will learn the polar plots in detail today. So we'll cover 4 different polar plots: the integrator, the differentiator, the type 0 first order system, and its inverse. So the frequency domain analysis basically starts with the need of the frequency domain studies. Let us have a basic idea what is the frequency domain analysis, why we go for frequency domain analysis. Any signal or any input supply voltage to a control system, especially a process where we are using a controller, this has to undergo a range of frequencies. So what is meant by the range of frequencies? Whenever a signal we are studying, we can resolve the signal into a series or into a combination of sinusoids or sinusoidal signals of different frequencies through Fourier series analysis or Fourier mathematics. So these different frequency inputs, which are basically in the form of sinusoids of different frequencies, will independently impact the system at its own. So if we try the different frequencies, suppose we take a frequency of 5 Hz, 7 Hz and 10 Hz, the three sinusoids coming at these 3 frequencies at some amplitude may be of value 2. So these 3 different sinusoids will impact the control system differently. But whenever a signal is given which is composed of these 3 frequency components of the sinusoids, the overall impact is seen or observed at the output of the process or at some point of the process or the plant or the loop. So this is very important to understand what these independent frequencies play the role in manipulating the system. So that is why we speak about the frequency domain analysis. Actually we are studying the system response for different sinusoids which would probably be having such frequencies in which the system is working at a given instant of time, because in real time we are observing that the system is moving from one time instant to another and giving some outputs, but in practical situation at every instant there are certain frequency inputs to the system or range of frequencies through which the system is traversing, and because of those different frequency inputs the system is behaving differently at the different instant of time. So this is not the time which is deciding the behavior of the system, but this is the frequency which is deciding the behavior of the system. That is why we are going for the frequency domain analysis. So we will have different techniques throughout the episodes which follow this session. We'll start with polar plots, then we will study inverse polar plots, then there are frequency domain specifications which we have to see to understand the system performance, then the Bode plots, then we will study the basic definitions which will be required to study the stability of the system, that is the gain and phase margin, then relative stability parameters. But these are the part of the frequency domain analysis. Again, when we will go for the stability studies of the system, certain more tools are there which we will use, which will involve both the stability analysis as well as the frequency domain analysis. So let us start with the polar plots. So we are speaking about certain plots which has to be considered when we are speaking about the frequency domain responses of the system. So in case of polar plots, we will take the loop transfer function, that is the GSHS for the system, and just for your convenience I would like to write it down GSHS, the loop transfer function we will consider. And here basically we are assigning S a pure frequency, that is the j omega. So in S, if you make the real part 0 sigma 0 and take the pure frequency component of S, then the system, that is a loop transfer function, will become GSHS for S equal to j omega. This is equal to G at j omega and HS j omega. Here we can express this in different forms. Suppose if I want to express in Cartesian form, then we will say that we have the real part of G at j omega, H at j omega, and again we have the imaginary part of G at j omega, H at j omega, like this. But at the same time we can represent G at j omega, H at j omega as G at j omega, H at j omega can be represented in polar form as the magnitude of G at j omega, H at j omega, and the angle of G at j omega, H at j omega. Now if we are drawing the polar plot for this, how it should look like? You have the real part of what? G at j omega, H at j omega, and the imaginary part of G at j omega and H at j omega. So in Cartesian form we can represent the real part as well as the imaginary part. So it can be shown in the Cartesian coordinates, but as well as the magnitude and polar plots can also be represented here. This is the angle and this is the magnitude. This is the magnitude. So any point on the polar plot can be represented by magnitude and angle as well as the Cartesian coordinates. So let us start with the integrator 1 by s. So as soon as we see that GSHS is 1 by s, we can readily assign s equal to j omega, so it becomes G at j omega, H at j omega equal to 1 by j omega. So interestingly it will become minus j into 1 by omega, right? So this 1 by omega is the magnitude, definitely, because if you want to take the magnitude around this, the magnitude will be 1 by omega, and you have minus j, which is equivalent to the angle minus 90 degree, like this, right? So if I want to draw the polar plot, how I will start? I take G at j omega, H at j omega for omega equals to 0 equal to what? This is having a magnitude which will be similar to infinity, and the phase angle is minus 90 degree, because that is a constant over here. Again I go for G at j omega, H at j omega for the case where omega tends to infinity. Then you can say from this expression you can find out that this is equal to 0 angle minus 90 degree. So we have to draw the polar plot where omega should start from 0, it will go to omega tends to infinity. So this is the real part and this is the imaginary part of g at g omega, h at g omega. Now when we start drawing at omega equal to 0, the value is very large, infinity. So we find a point here, and at the same time we see that when omega is very large, then the value is 0, but both at minus 90 degree. This angle is minus 90 degree for both the cases. So we start from here, go up to origin, and the arrow should be like this. So we are starting at omega equal to 0 and finishing at omega equals to infinity. So this is the polar plot for GS HS equal to 1 by S. So GS HS equals to 1 by S is the polar plot. Right. So similarly we can draw the polar plot for differentiator. So again we have to start writing very honestly g at g omega, h at g omega equal to j omega. So this should become equal to, magnitude is omega and angle is 90 degree. So you place g at j omega, h at j omega with omega equal to 0 angle 90 degree, and g at j omega, h at j omega with omega tends to infinity equals to infinity angle 90 degree. So how the polar plot should look like? This is the real part, this is the imaginary part, and at 0 it is 0 and infinity it is infinity, and angle is plus 90 degree. So the polar plot is like this, arrow is in this direction. Right. So one thing you have to be careful, that you see that the two transfer functions, that is the integrator and the differentiator, are inverse of each other, but their polar plots are not the inverse of each other. So if we try to be smart and we know the polar plot for integrator is this, so we assume that the polar plot for differentiator should be that will be a wrong idea. So you have to draw it honestly. So let us draw the polar plot for a type 0 first order system. So this is 1 by tau s plus 1. So we have GS at HS equals to 1 by tau s plus 1. So G at j omega, H at j omega equal to 1 by tau j omega plus 1. So here you have to rationalize the complex number. So how do you rationalize it? You multiply by the complex conjugate. So minus tau j omega plus 1 divided by minus tau j omega plus 1. This will give you a transfer function which is 1 minus j omega or j tau omega. Here you should have tau omega, j tau omega is the numerator, and denominator is 1 plus omega square tau square. So in this case we can say that g at j omega, h at j omega can be written in the polar form as equal to the magnitude 1 minus j tau omega divided by 1 plus omega square tau square into the phase. So the phase should be of the phase of the complex number which is available is 1 minus j tau omega. Right. So once we get this, we have to see that this phase is equivalent to certain value of tan inverse, which is determined through a special technique. So we know that this here the real part is positive in this direction and imaginary part is negative in this direction. So this is falling somewhere here in the fourth quadrant. So in the fourth quadrant tan is negative, so we have g at j omega h at j omega equals to mod of 1 minus j tau omega divided by 1 plus omega square tau square angle of minus tan inverse omega tau by 1 is omega tau. Again, the magnitude of this can be obtained as g at j omega, g at j omega, h at j omega equals to magnitude of 1 minus j tau omega is 1 plus omega square tau square divided by you have 1 plus omega square tau square angle is minus tan inverse tau omega. So this should be equal to 1 divided by root 1 plus omega square tau square angle of minus tan inverse tau omega. So once you got it, you can find out g at j omega for omega equal to 0, omega equal to infinity, and maybe some other values will also be required. So g at j omega, h at j omega for omega equal to 0 is how much? We put omega 0 here, so it is 1 by 1 is 1, and angle is, because omega equals to 0 over here, so we get angle 0 degree. Now g at j omega, h at j omega for omega equals to infinity will be how much? So for omega equal to infinity, naturally this denominator is very large, so this will become 0, and angle should be, according to this, minus tan inverse. So omega is very large, so it is minus 90 degree. This should be minus 90 degree. So we see the polar plot. Here is the polar plot. We have real part, imaginary part. Magnitude 1 angle 0 somewhere here. Magnitude 1, we say that this is the magnitude 1 and angle is 0, so 0. With magnitude 0 and angle is minus 90 degrees. So minus 90 degree means it is entering somewhere here, but we are starting from here. So from here we are starting and we are ending here. So how we can justify it? Let us have some value like this. We assume like this. So here it is starting with amplitude magnitude 1 and angle 0 and reaching at magnitude 0 and angle minus 90 degree. So what is the value in between? Let us try a convenient value. We put omega equals to 1 by tau. So if we write g at j omega, h at j omega for omega equals to 1 by tau, this should become, we are cancelling 1 omega square with tau square, so it should become 1 by root 2. Angle is, by calculation, it is coming minus 45 degree. Very simple. So minus tan inverse of 1 is minus 45 degree. So this is somewhere here in between. This is minus 45 degree. Minus 45 degree. So we can say that for frequency of 1 by tau, we are getting a point in between. Later we will check that this shape is a semicircle, right? So once that is verified, we can very confidently say that this is a semicircular shape. You are starting from here, with this arrow you show the direction, and this is the polar plot form for 1 by tau s plus 1. Now let us find the situation where the angle the Cartesian coordinate and the angle of the polar plot which we are speaking about is verified. That is, you are saying that you have the real part and the imaginary part. Here we say that this is the fourth quadrant, some angle theta is there, so this is some y and this is some x. So what are these values? We say that the magnitude is 1 by root 1 plus omega square tau square is the magnitude, and again we have the ratio y by x, y divided by x. This ratio is also known to us, and this ratio is tau omega. This ratio is tau omega by magnitude. So how do we determine x and y from here? So as you see, the magnitude is 1 by root 1 plus tau square omega square, so we can say that x square plus y square, this is the length, this is the magnitude. So x square plus y square is 1 by 1 plus omega square tau square, and from y by x we take y equals to x tau omega. So we can replace by x square plus x square tau square omega square equals to 1 divided by 1 plus omega square tau square. So we have basically x square into 1 plus tau omega square tau square equals to 1 divided by 1 plus omega square tau square. So x square equal to 1 divided by 1 plus omega square tau square, this whole square implies that x equal to 1 divided by 1 plus omega square tau square. So from here we can obtain that y equals to omega tau omega divided by 1 plus omega square tau square in magnitude only, because we are considering the magnitude, so we have taken x and y in magnitude, otherwise y is negative. So if we want to consider is it mathematically, then we have to take y as negative, because terms are squared, so this negative term will disappear. So here we will study how the information of x and y can be used in verifying that this shape of the polar plot is semicircular. So let us see. We have taken x equal to 1 by 1 plus omega square tau square, and y, if you consider the magnitude, then you can write minus omega tau 1 plus omega square tau square. So if we assume that the center is at 1 by 2, x minus 1 by 2 will help us in getting the equation of the circle. So plus y square equal to 1 by 1 plus omega square tau square minus 1 by 2 whole square, plus here the minus sign will vanish actually, plus omega tau minus omega tau divided by 1 plus omega square tau square, this whole square. So if you work it out, upon solving you will get into a situation where the left hand side will be equal to x minus 1 by 2 whole square plus y square, while in the right hand side only 1 by 2 square will be left. 1 by 2 square will be left. So this can be solved very easily with careful mathematical manipulations. We can resolve upon this. So with this evaluation we can say that we have a semicircle which has a center at 1 by 2 comma 0 and which has a radius equal to 1 by 2. So this question is very commonly asked during examinations, to draw the polar plot and verify whether it is a semicircle or not. So by this we can find out that this polar plot is very important from the point of view that other polar plots are generally governed by this design. So we have a polar plot, just a semicircle starting from omega equal to 0 to omega equals to infinity, and center is at 1 by 2, total length is 1, and this shape of the polar plot of type 0 first order system will help us in determining the polar plots of many problems where the factor is of the form of 1 by tau s plus 1. So further we will use this concept. Let us see how the inverse of this function will be observed. Sometimes you will feel that if this is the polar plot, then for the inverse it should be something like this, but this is a wrong concept. When the transfer function is the inverse, the polar plot again has to be drawn honestly from the fundamentals. So we have to use the same concept that we have studied. You take g at j omega, h at j omega equals to tau j omega plus 1, and you find out the magnitude and phase of this transfer function, which is equal to square root of tau square omega square plus 1. The phase is simple, the imaginary part divided by the real part, the tan inverse of this, and as this is the first quadrant, so naturally the tan angle is positive. So tan inverse tau omega will be the angle. So we have to honestly place the values for g at j omega, g at j omega, h at j omega when omega equals to 0. You should get the magnitude of 1 and angle should be 0. When we take g at j omega, h at j omega with omega tends to infinity, you will see that magnitude is infinity while the angle is 90 degree, as we all know about the tan function. Now the interesting part is that if you take the real part of this function, that is a real part of g at j omega, real part of g at j omega, h at j omega, this is equal to how much? 1. While the imaginary part of g at j omega, h at j omega, this is equal to how much? Equals to j omega. So the real part is constant and imaginary part is variable. So when we are drawing the plot of this, you see how we can draw the plot of this real part of g at j omega, h at j omega, and imaginary part of g at j omega, h at j omega. You have to write exactly like this in the examination when you write the answer. So your real part is fixed, this is equal to 1. Imaginary part varies. How it varies? Theta equals to tan inverse of omega tau. So naturally theta for omega equals to 0 is equal to 0. Theta for omega equals to 1 by tau equals to tan inverse of 1 equals to 45 degree, and theta for omega tends to infinity is equals to 90 degree. So naturally this should be a real part constant, imaginary part varying as omega t varies, and at 45 degree you should get this value, right? So the polar plot of tau s plus 1 is exactly different from the polar plot of 1 by tau s plus 1. We have to keep this in mind, because whenever we get the questions in the examination we have the temptation to commit such mistakes. So for today this much is the portion, and in the coming session we will discuss the polar plot of the second order system model. If you find this session useful, you can press the like button, and if you want to stay in touch and follow through in all the episodes coming, then you can subscribe this channel. Thank you for listening.